Hey, what's going on? Welcome to my channel. Today I want to talk about waves because, in my opinion, there's a lot that can be said that I just don't really hear people talking about. Of course, there's probably subjects discussing it in very nuanced ways or very closed communities or whatever, but in all of the education that I've received on the internet and in school, nobody really talks about the things in my head regarding waves currently. So there's a few different things that I want to talk about. And it's all kinds of waves: water, light, maybe sound, and gravity. First, I want to talk about water because it's a really good example. It's a really basic, you know, down to earth example. When you step into a pool of water, you just glide through it. There's no real resistance, at least for human bodies. There are different, buoyancies and stuff like that for different chemicals and so on. But generally speaking, if a person steps into a pool of water, they will go through it. They just, especially a whole body, not like a liquid. It's a more nuanced if we're talking about liquids. But so, like a solid body object in water, you just put it in water and it goes through. No big deal. But as soon as you, for example, jump off a really high bridge or skydive or something into a body of water, it becomes solid. I think it's very important to know this or note this fact that water and other material, other elements, or you know, other things in life behave similar. Waves specifically, I mean, light behaves this way. I'm not sure about sound. I haven't thought too much about sound, to be honest. But I speculate that gravity behaves this way as well. So the next thing I want to do is to give you a simple demonstration of things that wave, I guess. So I have a pencil in my hand. I can give it some velocity and stuff, but for the most part, you can see it. You know where it's going. It is very, I don't know, easy to calculate, I guess you would say. Like there is no extreme forces being put on this pencil. Even though it is moving, the position is changing. There are velocities. But you can see it. It exists. You see every photon emitted from this pencil, moment by moment. More or less, pretty much. But if I wave it around very fast, you can see I'm doing it in front of the screen. Of course, frame rate plays a role in this. But even if you were in my, me and you in real life, you would still experience this invisibility, I guess you could say, property of motion or matter, mass. What do you call it? Momentum. And I thought about it. I thought about how, generally speaking, when you just watch me do this, you're not going to see too much of anything. It's almost invisible. If I were doing this, there's a frame rate, so it is this little demonstration is limited to the frame rate that the camera's recording this video at. But if I were doing this in front of you in real life, and you had your perfect perception versus this video, you would be able to move your eyes and at the direction while this is moving, and once in a while you will catch a glimpse of the pencil in its entirety, whatever place that it's at that moment. You can do this with things like wheels or a fan on your ceiling, anything that's moving that's relatively fast, but not too fast, but faster than your, I don't know what you call it to be honest, but than your ordinary eyesight. If you move your eyes and catch it at a particular place and time, you will then see that pencil or wheel or fan or whatever that you're looking at in that very particular moment. And I think this helps demonstrate what a photon is, and also how we could potentially detect a graviton if gravitons exist. So, with photons, in my opinion, that's kind of the difference between a photon and an electromagnetic wave. Is you have a very fast wave. It is very well, most of the time, not all of them. They're different wavelengths and different frequencies, but light is very quick, and just generally, light is quick, and I'm pretty sure that the light we see is fast, but there's even faster light, more intense light. Either way, it's very quick. It waves quickly. But we have ways to detect when a particular photon interacts with the detector. Also, I've learned that I guess the real reason why the double slit experiment is, in my opinion, kind of a failure, in the sense that it doesn't actually describe consciousness. It's just so. What I learned was that the detector used to determine which slit a photon travels through in the double slit experiment is, there's a few different devices, but essentially the device used, what it does, it doesn't just look at the slit, which is what was kind of not suggested, but I guess implied when you first learn about the experiment. A lot of people just kind of brush over that fact for some reason, which I think is misleading, honestly. It would save a lot of people a lot of trouble if they just mentioned that fact, because that's I maybe I've learned it in the past, but most people don't talk about it. So it's not this like very well known. I haven't even described it yet, but I'm just saying this fact, or this fact that people just brush over when they discuss the double slit experiment. It's very misleading. Um, I don't know why they do it, but basically what I'm saying is the detectors used to see which slit the photon traveled through, they don't just look at the slit. They use photons, or what, I don't know exactly, but I think it's photons. They use photons to interact with the slit that they decide to observe, interact with the photon passing through it. So they see the photon by interacting with it. At first glance, this is a misleading fact because everybody's talking about consciousness and quantum mechanics, and like it's so woo woo, and then you bring up this fact and it's like, oh, so they're not actually, and they're not changing the probability by observation. They are altering the probability by interaction. And it is a valid experiment in that when you're honest about the results of it and the mechanics behind it, it's a fair valid experiment to be done. But the misleading fact causes a lot of miscommunication. But there is something of value, I think, in this misleading fact, and it is that the photon being interacted with as it passes through the slit is the same exact idea as what I was just discussing about catching the glimpse of light at a particular moment. That's essentially what uh, the detector is doing. It is also interacting with the particle, but it has to obviously catch the particle. It has to meet. So there is this property of waves that allows them to be captured at a particular moment. And when you do, you get one single frame out of it when you're talking about fast moving waves or fast moving objects, fast things that are faster than the eye can see, essentially. Um, and this is the same exact thing with the photon detector on the double slit experiment. You're detecting a particular moment in space time where that photon passed through the slit. And so you get that image, whatever the interaction happens to be. I don't quite know that, but um, and then of course when the detector interacts with the photon, it interrupts the wave, the probability wave specifically, but the wave, what do you call that? I don't remember a term for it, but I'll just use probability wave for now. It interrupts the probability wave that should have been emitted after it passed through both slits. The wave passes through both slits. And what the detector does is determine when the wave passes through the particular slit it's looking at, and then it catches that photon, it interacts with the photon, and it disturbs the waveform. And as I understand it, presumably once that photon that was detected passes through the slit, it is the photon responsible for the detection on the actual detector. versus if you detect a photon through that slit and then it lands somewhere completely irrelevant to that detection, which would actually be just as interesting if you interacted with the photon and because you interacted with it, it got turned off course. I'm not sure. I don't know if scientists are accounting for that or if it really is just they interact with the photon and then it lands where it should have landed. I don't know that. But then there's gravity waves. So far, what I've described is this sort of ability to, in my opinion, it's kind of like riding a wave because you have this. I have a pencil waving in front of me. It's just waving. And what you want to do is catch the wave. You want to observe wherever the pencil is going at that particular moment to catch that particular moment in space time, to see it. And so I would call that catching the wave or riding the wave. And then if you want to detect a graviton, if they exist, you would have to do something similar where you're observing the wave, which is I don't know how you would begin to do this, but so you have LIGO, it detects gravitational waves by having two very large beams of light shift in and out of phase due to um, gravitational waves bending space time. It's a very interesting experiment, actually. I'm not sure exactly how you would catch the wave with LIGO. I haven't thought about that, but I think that's a good place to start is by observing the gravitational waves felt by Earth, detected by LIGO, and then managing to find a way to catch and ride that wave and determine a graviton out of it. I brought up water in the beginning because I wanted to talk about the properties of waves and how you could have light that just goes through matter for different reasons, but for better or worse, you could say that light goes through matter. Um, there are times where light is transparent, where you could just move right through light. For example, there's visible light. You're not experiencing any particular force emitted by visible light. You just walk around on Earth and you see things, but there's no punch to visible light. Thankfully, we don't experience X-rays on Earth. But under very intense and extreme situations, light and other particles, very tiny, very fast moving, can uh, can I don't know a good term. I want to say explode, but collide. That's what I needed to say. They can collide and burst. They can become solid objects, especially in regards to each other. Not so much when you're like trying to shoot a single photon at, I guess, a sheet of metal. It's a little bit different, but especially in particle interactions, they become very physical, at least the way I understand it. Um, and so it's no longer just light being a sort of wave that phases through matter. Light and other particles can be very physical with each other. And of course, all this has to do with waves, anyways, because of fields that everything exists on, light being electromagnetic fields. And so I think velocity has a lot to do with the way that you intend to interact with the wave. And also, I think it's important to consider the velocity of a wave in regards to scale, uh, because I've noticed it's very similar in the way when we're talking about speed, velocity. For example, when you watch a wheel spin, something spinning in a circle, you can see it get faster and faster until eventually the physical properties kind of become invisible. Um, but what happens as acceleration increases, it appears as though it is slowing back down, which is actually interesting just in terms of space time. Just on that frontier alone, it it's very interesting to discuss that because when we talk about um, space time in general and special relativity, the faster you go, especially approaching light speed, you will appear to slow down. You will Space time will condense, and from an outside observer, they should moving at high speeds. They should see that the space time around your I don't know your person is condensed, and from a internal perspective, space time around you has flattened like a pancake. Everything's stretched and it just seems very flat. Your I think if I'm not mistaken, your field of view becomes wider as well. But either way, yeah, field of view becomes wider. Everything gets flat. So, but that's just an interesting side note. Um, what I really want to talk about is waves and the way that speed works or velocity. You see something go faster. You see a wheel spinning, and it'll appear as though it slows down. And then as you keep accelerating, it'll appear though it's speeding back up again. And I believe this back and forth um, appearance continues as you accelerate faster and faster. I'm guessing. I don't know quite the details behind that, but from my experience, it goes fast and then slow and fast again slow as you accelerate, and then when you decelerate, it reverses. I just feel as though there's this um, correlation between the way things appear to move versus how fast they actually are moving, and the way we view waves. Interestingly enough, we hypothesize that the universe is expanding faster than light. I think those are just by calculations, though. I don't think we are observing directly the expansion of space time. But if we were, it might appear differently than a calculation might give. These are just some of my thoughts that I really wanted to get out because this stuff is mind-boggling. It's mostly just me trying to make sense of it, but I also feel like these are some pretty valid or interesting perspectives that I just don't see or hear anybody talk about really. So, anyway, thanks for watching. Bye for now.